Hi, my name is Galen Harrison, and I'll be presenting our paper, JupyterLab in Retrograde. I'm a PhD student at the University of Virginia's Biocomplexity Institute and Initiative, and this work was done with folks from the supergroup at the University of Chicago. It's been pretty well established by prior work that doing data science requires making a lot of tentative decisions about how to handle data. These can be things like what variables are relevant, how to handle different kinds of missing data, and how to regularize inconsistent data encodings. How these issues are handled can have dramatic effects on analyses or models that are downstream of them. However, how and whether a particular decision by a data scientist will have an impact is hard to know ahead of time. A decision about data cleaning can impact the importance of different features, for example. The impact of these decisions becomes particularly salient when thinking about fairness. The importance of features can influence how the model works. Data scientists who make tentative decisions about data processing early on may have no reason to go back and revisit those decisions. They may not realize the impact their decision had and whether, for example, their decision led to unfair outcomes downstream. However, most AI fairness tools are focused on auditing models after they have been created, at the end of the process. At this point, the decisions about how to clean the data will have already been made. Therefore, data scientists may be unwilling to go back and re-examine those decisions. Because of this, we hypothesized that data scientists who received contextual notifications about the data processing decisions as they were making them rather than at the end would make more careful decisions about which would lead to more fair models. I'll cover what we mean about contextual feedback in more detail later on, but an example is a message to the data scientist highlighting potential proxy variables defined within the computational notebook being used. By nudging people with relevant information about potential fairness impacts throughout the process, we hope to help data scientists make more careful decisions about fairness. In order to do this, we implemented Retrograde, a JupyterLab notebook environment. Retrograde analyzes the data scientist's JupyterLab notebook while they are working on a data cleaning or machine learning task and provides them with contextual notifications. We then used Retrograde in a between subjects online study where we asked participants to complete a data cleaning and machine learning task with Retrograde enabled. We found that Retrograde helped data scientists make more careful decisions about what data to include and reduce disparities in the model. We also found that it made participants less comfortable deploying their model. What kinds of notifications might help a data scientist make more careful decisions? Here's an example of some data that a data scientist might make a model with. However, there are several aspects of this data which could pose fairness issues if handled incorrectly. One issue might be that the data contains features which are inappropriate to use as the basis for decision-making, such as race or gender. A data scientist may end up using these features either without realizing it or without realizing that it is inappropriate to use. There may also be features which are appropriate to use in some contexts, but inappropriate in others, like age. A notification about the presence of these features may help a data scientist exclude these as predictive features or use them as the basis for auditing other aspects of the data or model later on. There may also be columns which are proxies for protected attributes. These may or may not be acceptable to use. A data scientist must make a decision about whether to use these columns or somehow correct for their association with a protected attribute. Another issue might be that there is a pattern of missing data. If missing data in one column is correlated with membership in a protected group, then how this data is handled can have an impact on the model that is produced. Data scientists may not notice that these patterns exist and may simply drop data with missing entries, potentially creating disparate impact. The relevance and impact of these issues can change as the data scientist goes through the iterative process of developing and refining the data. Suppose the data scientist drops a column, does some kind of imputation to correct for missing data, and then splits the data into train and test datasets. The aspects of the data that are relevant to the task and therefore relevant to task fairness then change. This means that making automated notifications about these properties requires reading the data as it exists within the notebook session. Here, train and test do not have the gender column anymore and have had age imputed. Retrograde can examine the contents of data frame objects to do this kind of inspection. Retrograde also automates aspects of fairness auditing. Suppose that the data scientist built a model and uses it to predict values for rows in the test dataset. Auditing these predictions for fairness requires labeling rows in test with the protected attribute. These protected attributes are not present in test, but can be found in DF, the original data frame. To do this requires tracking relationships between different data objects. If the process of making the training data involves complex data transformations, to do this auditing would require significantly rewriting code. An automated notification about disparate impact would need to trace backwards from the feature data up to the nearest data with the protected column and try to match the rows in the test to the rows in DF. We built Retrograde to be able to do this on a best effort basis using syntactic analysis of Python code. A complicating factor for this task in the notebook setting is that the code that produced a particular data object can be changed or overwritten. If the data scientist decides that they want to try a different set of features, they might execute code that redefines df to refer to a different data object. Now, the relationship between gender values and the model is the same, but within the notebook environment, there's no way to access those values since df has been overwritten. To handle this, we develop a way of versioning and tracking data and data ancestry. We built our notifications on top of these analyses. We used JupyterLab 1 and a custom JupyterLab kernel 2 to create a history of notebook interpreter state. The state was combined with analysis of code executions performed in 3 to identify connections between pandas data frames and scikit-learn models. These analyses were then used to generate contextual notifications to the user. So what did we say in these notifications? This is a normal JupyterLab interface with code cells in the middle. Our notifications appeared on the side of the notebook environment with the option for users to click on them to see an expanded view. They did not block the user from taking any action, and the user is free to ignore them entirely. It is important to emphasize that these notifications are not meant to lint notebooks for fairness issues. Linting would mean asserting that there's one single correct action to take, which is not always the case for fairness issues. Clicking on the orange notifications would lead to a larger window with additional information about the notification and context-specific information about an aspect of the data or model. The one shown here is an analysis of missing data patterns in the data frame. We provided text describing the pattern the note was looking for and why the pattern might be important. Because we did not want to build a fairness linter, we tried to avoid making prescriptive statements in these notifications. In the notes, we provided information about the pattern or patterns identified within the notebook. Here, the note reports that there are 3 patterns of missing data within a data frame called loans that may indicate a fairness issue because they are correlated with a protected attribute. The numbers are calculated and updated based on the actions the data scientist takes. We built 5 different notifications, each of which provided the data scientist user with information about fairness-relevant aspects of the data they may not have noticed. We built the protected column note, which analyzes data frames in the notebook and made guesses as to whether any column included data which encoded something like race or gender. This note let the user look at the guesses and correct incorrect guesses about the columns. These determinations were used in several other notes. The proxy column note looked at columns which were strongly correlated with the protected columns as determined by the protected column note. We've already discussed the missing data note. The model report note tabulated performance metrics by protected groups in order to identify disparities in model performance. This note worked even when the data encoding the protected groups was not included in the features fed into the model. The counterfactual note tested whether a model was robust to small perturbations in feature values. We wanted to see if these notifications would affect how data scientists worked if they were received while the data scientists were working, after they had finished, and if they did not receive any notifications at all. To do this, we conducted a between subjects online study where we asked participants to use data to build a model. We asked participants questions about their attitudes before, during, and after they had completed the task. Participants were asked to build a model that would be used for automatic loan approval decisions. We had created a synthetic dataset with a predetermined data issue that they would have to solve in order to make a model. This dataset was a loan dataset in which Black applicants had a much lower approval rate than other applicants. At the end, we asked participants to identify the model in the notebook they believed to be most appropriate. We recruited participants using the online platforms Prolific and Upwork. After screening for experience and removing participants who failed to finish the task, we had 51 participants in total. Our participants tended to be well-educated, and a large proportion of them reported working in data science, data analysis, and machine learning. There were 3 conditions. Continuous, those who saw notifications throughout the process. Post facto, those who saw notifications at the end. And none, who saw no notifications. We structured the task into 5 sections: data exploration, data cleaning, feature engineering, model training, and model selection. We had 17 participants per condition. Because this population is hard to recruit from, we cannot make generalizable statistical claims, but rather provide a qualitative, holistic evaluation of user responses and behavior. The first thing we looked at was whether participants used protected attributes like race or gender as predictive features to the model. While data about these attributes may be necessary for auditing or making corrections, using them as the basis as a decision is in many contexts unfair or illegal. Participants who received notifications at the end or no notifications were surprisingly likely to use race or gender as predictive variables. 12 out of 17 participants who received no notifications and 11 out of 17 participants who received notifications at the end used race or gender as a predictive variable in their model. By contrast, only 5 out of the 17 participants receiving continuous notifications did so. Through coding responses to our questions, we found that participants in continuous cited retrograde as their reason for taking certain actions. Participant 27, who saw notifications throughout the process, stated, "The information from the notifications made me reconsider using race and gender directly in the model." Analysis of the responses shows that participants in none and post facto were aware that they used these features, but chose to do so anyway. We observed that participants in these conditions, without continuous notification, tended to start with as much data as possible and defer examination of the effects of that decision until later. One participant, who used race and gender as model input, stated, "It makes decisions using race and sex, so that can't be exactly fair. The biggest indicator of a loan being turned down was race." Despite the fact that participants in none and post facto were aware that these features posed issues, they did not take action to remediate it. We found that notifications, regardless of when they happened, also changed attitudes participants had towards their models. We asked participants about whether they'd be comfortable deploying the model they had developed. Here we showed the percent of participants who saw no notifications who reported strongly agreeing, agreeing, not sure, disagreeing, strongly disagreeing, that they were comfortable deploying the model. Around half of these participants said that they would be uncomfortable deploying the model, that is, they disagreed or strongly disagreed. However, for continuous participants, 65% said that they would be uncomfortable, and for post facto, 76%. Furthermore, nobody in continuous reported being very comfortable with deploying the model. Those participants who saw notifications were less comfortable deploying the model than that they had built. Furthermore, the reasons participants gave for this sentiment varied. Participants who saw no notifications were likely to cite factors related to model improvement. However, participants who saw notifications were more likely to cite fairness as the reason for their discomfort with the model. Other results we found were that participants who saw notifications throughout the process tended to have fewer or less severe disparities between racial groups in their models, while suffering no penalty in overall performance. They were also moderately more likely to address missing data issues in a nuanced manner. Another key facet of retrograde is that it automates certain aspects of fairness auditing, which would be cumbersome to implement by hand, and we found that nobody in none or post facto replicated any of the analyses performed by retrograde. We did find that in their responses, participants were sometimes frustrated by the lack of specific guidance. We set out to look at whether contextual notifications throughout the data science process could get data scientists to make more considered decisions about fairness. To test this, we built Retrograde. Our findings show that notifications throughout the data science process do seem to help data scientists make decisions which are fairer. However, this potentially leads to frustration with the much larger amount of uncertainty. Future work should look at developing more nuanced ways of developing notifications that more effectively manage the data scientist's uncertainty while also promoting critical ethical reflection during the data science process. Thank you for watching.